So what do you expect if you're measuring conductance? Well, if you have two dots defined by two gates, right? Dots defined by different gates, say gates 1 and 2, tuning the energy levels of the dots. Okay, so these gates 1 and gate 2 are tuning the energy levels of dot 1 and dot 2. You only get conduction when the energy levels of both dots line up. Okay, and they both line up only at certain points, like here and here and here and here. And actually, the black points and the circle and the white points are bonding and anti-bonding states. Right? So you get conduction when at these certain points when the energy levels line up and nothing in between, and then these numbers tell you how many electrons are in any given state as these energy levels line up. This is what you theoretically expect. When we measured our double dot system, this is what we saw, this honeycomb pattern pretty much as predicted. And this is really exciting for us because it showed us we had really complete gate control over a double quantum dot system in a nanotube. So now we can really study all these different bonding states. So again, here you can see we get conduction, these conduction peaks, these bright spots when the energy levels lined up, nothing when the energy levels didn't line up. Okay? We could do further studies, these look very carefully at the vertices. There's all sorts of predictions as to what you're supposed to see, what these energies mean. We extracted things like the capacitance of the nanotubes to each other and to the gates and the interaction energies. You know, these numbers don't mean much. I'm not putting him here to go through it all, but just to show you that once you could have this level of control, you can really start extracting information from these systems and studying them in more detail. Okay. And there's an application. As I mentioned at the beginning, there are things like quantum computers, right, that we're interested in. That's why one of the motivations for measuring these mesoscopic systems. And there's even a prediction for making a quantum computer out of a nanotube, right? And the idea is this, is that you have this orange thing is the nanotube, okay, and then these yellow lines define quantum dots. Okay, and then 3 quantum dots form a qubit where you have spins. These arrows represent spins, and the different spin states interact and do computations, and this is a quantum computer made on a nanotube. And it's nice because it's sort of a linear, scalable computer. And if you can get one to work, maybe you can get many to work, and you can do all the calculations just along in this really nanoscale system. And as you notice, this idea of this schematic for a quantum computer looks pretty similar to the actual devices that we've been making. Okay, so we're actually getting closer to be able to do these sort of computations. And in fact, there's a recent paper that the group that I came from, the postdoc, has actually been able to do some interactions between qubits in this sort of system already on a nanotube. Okay, so that's it. I hope I've given you a sense of what this sort of mesoscopics research is, of what sort of devices you can make, and why it's interesting. As I mentioned before, there are 3 questions that we're continually asking. You know, how are small dimensions different? And the answer is that they're very different. Electronic properties are really different on the small scale. You can see things like coherent transport, Fabry-Perot I showed you. You can see transport of single electrons. You can see quantized conductance in 1D, things you would never really see in the macro scale, but are really fundamental and interesting and maybe even relevant to devices on the nanoscale. You know, can we see and study quantum properties? Yes, of course. In fact, quantum properties dominate at these scales. All of these things are really quantum mechanical. Right? Quantum mechanical events, we're seeing electrons as both waves and particles. We're seeing interference between electron waves. We're seeing energy quantization. These things are crucial at these small scales. And can we make novel ultra-small devices? And again, yes. You know, the simplest nanotube is a field effect transistor. We can see single electron transistors. We can build up to things like quantum computers. Right? We can do a bottom-up approach to making these devices and try pretty hard to use new technologies to configure systems to make even more advanced devices. And in general, I think that nanotubes are really model systems for studying these things, very versatile and fun to work with and think about. So thanks again. I'll end with a picture of the people who actually do the work, not me, them. and let me know if you have any questions. Thanks. Yes?
You have mentioned the quantum confinement of the electrons.
Yes.
And the change in electron properties. I just wonder, since for photons in such a small structure, there will be quantum confinement of photons as well.
Phonons? Yes. Yes.
And photons can interact with electrons.
Yes.
I just wonder, do you see whether there will be a large effect of the confinement of photons on the electron properties, or don't think there would be?
Yeah, that's a great question. It turns out that because of the structure of nanotubes, phonons are relatively weak at low temperatures, and so the phonon energy scales, you know, where you see just thermally affecting, thermal phonons is typically, I don't know, give me above 100 millivolts, and I don't know how, but I don't want to convert that to temperature, but much higher. We're typically working at the sub-millivolt scale, so maybe 100 times higher energy range is where you expect to see any influence of phonons. Now, there might be phonons at lower temperatures, but those are expected to be quantized at any regime where we're working, where we're actually looking at electronics with the nanotube. So it turns out that electron-phonon interactions at these temperature scales are pretty weak, which is a big advantage for these quantum systems, right? So you're not losing energy or coherence or any of these things to phonon interactions. Yeah. Now one thing that people have done in tubes, which I find really interesting, they've suspended nanotubes over trenches and actually looked at the quantization, looked at quantum fluctuations of the nanotube, just vibrational modes of a nanotube. And they've actually seen some influence of phonons in that case because they're actually just moving the lattice a little bit, but it's not as relevant in electronics. Yeah. So, yeah.
Well, it seems that recently research on graphene is very hot.
Yes.
Any papers about graphene can be published.
Yes.
How do you compare graphene research with nanotube research?
Yeah.
Why is graphene so hot?
Yeah. so I don't know, for those of you who don't know about graphene, so I mentioned that carbon can be formed into sheets, and those sheets are usually stacked as graphite. And someone recently discovered how to make just a single layer of graphite. And that was thought not to be able to be physically possible because a 2D film should be unstable. It's thought to just wrinkle or just have fluctuations that made it effectively 3D. And yet someone is able to stabilize it with this highly advanced technology using Scotch tape. Right? So you take a piece of graphite and you put a piece of Scotch tape on it and you pull off the top, and these things cleave very easily because they're layered. And you take that, your tape now has a freshly cleaved layer, and you stick it on your substrate and you peel it off again, and you look at it very carefully and you find graphene, single layers. Right? So that was discovered about 4 years ago, and there's been an explosion in papers. I went to this big physics meeting, and I would say, this is almost every physicist in my field was there in condensed matter, and probably 10% of the talks were on graphene. That means like 1 in 10 condensed matter physicists is working on graphene. Okay, I don't know if that's a real number. That was my feeling there. So one question is, why is graphene so hot? It's new. That's a really big thing, right? I mean, in physics, you're always looking for something new. So if you don't have a new technique, a new material is a really good thing. So one of the things you see is that graphene's really easy to make. Anyone can make it, and it's new. So if you have a technique or have anything you're working on, you just put in graphene. Right? So we've done that too. We were looking at superconductivity in nanotubes, and now we're just looking at superconductivity in nanotubes and in graphene. Okay, so that's one of the things. It's really easy to substitute it in. So, and if you've worked on things like nanotubes, the fabrication techniques are very similar, right? If you've worked on any sort of mesoscopic structure. So that's, again, as you say, it's a new material. Lots of things may publish. It's sort of a steamroller effect where the more people publish, the more people are willing to publish, the more people are just doing anything on it. So, it's unclear how long that will last. But graphene does have some interesting properties. It's gate tunable metal in some sense, right? It's a semi-metal that you can tune with a gate, and so it may be applicable to making, a transistor substitute. If you can make if you can pattern sheets of graphene, it's all gate tunable, so you can really make transistors in an easier way than you can with nanotubes. You really have to place in certain locations. So that's one big motivation for looking at it in terms of electronics. It turns out that its electronic structure, the Hamiltonians that describe the electronics in graphene are identical to those that describe photons, right? So it's a way of looking at like photon physics in the solid state. So it has a Dirac equation that is similar to the Dirac equation for high energy physics. So people are thinking of all sorts of high energy experiments that can be tested in graphene. So one thing is it can tunnel through barriers that are much thicker than you'd otherwise see tunneling through, and that's been actually tested. Klein tunneling, I'm not sure what it is, but that's been actually shown recently.